Welcome everybody to the last session of EuroBioc 2020. So as usual, we're going to wait a few seconds before starting so that everybody can join. And then we're gonna get started. So just in the meantime, let me remind you what Charlotte said earlier, that a group of us will sort of hang around in the platform after the conference. Maybe like grab a few tables and have informal chats. So, and I think Henrik will join as well. Hopefully, we'll see. Yeah. So yeah, stick around if you want to kind of relax and decompress after the conference. So well, I see the numbers still are going up, but maybe in the interest of time, I will start with the introduction. So it is my great pleasure to welcome our last keynote speaker for the conference, Henrik Bengtsson. All right, Henrik is first of all, is a friend, and second of all, he's an associate professor of epidemiology of biostatistics at UCSF. He's also a member of the R Foundation and the R Consortium Infrastructure Steering Committee. His research is focused on biostatistics and bioinformatics with emphasis on high quality reproducible method development at a large scale. And perhaps to this audience, he is more famous as a R developer, and he contributed over 30 R packages both in CRAN and in Bioconductor. I have to say, I before meeting him personally, actually, I knew Henrik from the Aroma package and project, and actually he came up with the Aroma project before Nespresso's Aroma, so you should maybe claim for but I think now the Aroma Lite package is still in Bioconductor after 14 years, and is actually still one of the dependencies of my one of my packages. But maybe most other people in the conference know him for the metric stats package, which I think everybody here has used at least one time. And then, of course, you have seen his name and RHelp, RDevel, BioCDevel. He's very active and very good at helping the community and answering questions. So I think we are at 50 attendees now, so I can safely give the stage to Henrik, and I'm really looking forward to his presentation. Henrik?
Thank you very much, David, and thanks you for the kind words and introduction. So yeah, I just realized the other week that I've been using R for 20 years now. It all started in a project in school or at university. A friend of mine said, "Hey, there is this cool thing called R. Are you sure you want to keep working on MATLAB?" Which I claimed myself to be an expert with, and after some struggling, he convinced me to do the homework in R, and it took me 2 days, and I completely switched. I fell in love, open source and everything. So it's and speaking about those 20 years, I think Bioconductor project started almost 20 years ago, and it's been a pleasure to be part of it. I was much more active about 8 years ago. I followed actively. I wish I could spend more time, but it's really nice to see how amazing community is, and teaching and friendliness and all the amazing science that comes out of it. So I hope there will be at least another 20 years of Bioconductor. Going back about 15 years ago, so I've been spending most of my research in applied statistics and genomics. So I did two-color microarrays when those came out, Affymetrix, Illumina microarrays, and as David mentioned, the Aroma project grew out of that. So about 2005, built the Aroma project so you could process like literally an infinite number of Affymetrix microarrays on a small laptop. And the seed of what I'm talking about today, parallelization, grew out of that 2005, 2006, where I needed to scale things up. Me and my collaborators on Linux with big compute systems, on Macs and Windows machines. Everything is needed to be supported. So today I'm going to talk about the core of that. It's the future framework. It's a simple, extendable, generic framework for parallel processing in R. And so let's say, why do we do parallelization? So that might be useful to clarify. Most of us think about parallelization as speeding up things. So if something takes 10 hours, you can use parallelization to finish within 1 hour. That's about wall time. Another reason, which is related to this, is you might actually not be able to process everything in memory on your local machine. So the strategy we do there is we split it up in smaller chunks and combine it later. And by splitting it up in smaller chunks, we have to process it over time. We could also parallelize out to multiple machines. So in that sense, lowering the memory requirements, parallelization can help too if you have multiple machines. We also have the reasons such as user interfaces. So if we run some heavy task, when we click a button, we don't want that task to freeze your user interface. So you want to spawn things off in the background. So there are different reasons for parallelization. Let's look at what R has already available. And I should say that this talk, I'm trying to aim at both people who never done parallelization, thinking about it, has done it, has went through all the hoops and hurdles trying to figure it out, or even people who design parallelization frameworks themselves. So hopefully you will see something that you like here. So the history in R. It's so let's do a small toy example here in the bioinformatics world. So say I created a package called DNA-seq, and I have 3 FASTQ files, the sequence data, and I want to align them. And my package provides a function called align. So I can use the base lapply function to iterate over those FASTQ files and call align on each of them. And each FASTQ takes about 1 hour with this function to align. So it will take 3 hours to complete here. So if you look at the parallel package that you all have in your R installations, there's the mclapplyo function, multi-core lapply. It works very similar to lapply, and you specify the number of cores you want to parallelize over. So if you have 3 cores available on this machine, we can use those to parallelize these FASTQ files at the same time. So this will finish now in 1 hour wall time. Of course, there's 3 hours worth of work happening, but it finishes in 1 hour. This works if you're on Unix or Mac. If you're on Microsoft Windows, R doesn't support forking there, so it will fall back to the basic lapply and run sequentially. If you want to support Windows as well, there's a solution for that too. It works slightly differently, where you explicitly create a cluster of workers. Here I create 3 workers, and they spawn off R sessions in the background that wait for task to be run. And the first thing we need to tell those workers is to load the DNA-seq library. And after that, we can use the special function parallelization to distribute that alignment call for each of the FASTQ elements. And this was also then finished in 1 hour. So these are the basic alternatives we have when we work with R. Okay, there are a few things we need to be aware of. It's so mclapply is magic, but it does actually have some problems. And it's great because it works exactly like lapply. It comes with all R installations. So if you use this, you know everyone will have it. You don't have to worry about global variables and loading packages because each of the parallel workers will have an environment that's identical to the main R session. And this is based on a concept that in operating systems is called forked processing. So it's done by Linux and Mac OS. Windows has that too, but it's not supported in R. Unfortunately, forked processing can be unstable in certain situations. So the multi-threaded code, that's not multi-process code. Multi-threaded code is like a much low-level parallelization framework that you see in native implementation. You can do that in C and C++. OpenMP is a word. pthreads is another one. If you have code like that, that code might not be stable to run in forked processing. So you might get very weird crashes, hard to reproduce. Graphical user interfaces can also struggle with forked processing. And there's been report, for instance, that RStudio has been crashed because people use mclapplyo. It's not just an RStudio problem, but it's an example. So we have to be careful when we use mclapplyo. Parallelization, though, it works everywhere, but it takes some more efforts. So works just like lapply, and it works on all operating systems. You have to do, as you saw in the first example, you have to tell each worker to load the libraries. So you have to do a cluster evaluate. You might also have to export objects over to the worker. That's cluster export. So it's a bit more tedious, more verbose, so to speak. And if we look at, so now picture yourself as a person who want to add this to your package, parallelization. We can go look at CRAM package and Bioconductor packages and see what's been done before. And you will find a few different styles of introducing parallelization. So if you're on Linux and Mac, you probably go to the mclapplyo first because it's so simple. So let's consider this simple case where I want to write a function called align all, and that will just encapsulate and hide that lapply call. So in my sequential implementation, it looks like this. I just pass the vector of FASTQ files, and I call lapply on that, and then that will call align over each element. And the user would just call the function align underscore all on the FASTQ files, and it will work as expected. Now, if you want to parallelize, your first attempt might be like this. You provide an argument, an additional argument, say parallel equal to false. That's the default here. But if the user want to do parallelization, they can specify that as an argument parallel equal to true. And what happens in the function is that if you do conditionally, if you do parallel, it will call mclapplyo. And in this case, you choose to say, let's parallelize as much as you can. And you use all the cores available in the current machine. So you call detect cores. And if the user didn't want to parallelize, they will end up with a regular lapply. So this is a nice introduction to parallelization. The problem with this detect cores, we can talk about that afterwards, but it hijacks everything. So it's not very friendly if you run another thing on the same machine, or if there are other users running on this machine. So avoid using this one, I would say. Better is to do this. If you don't specify, it turns out actually that mclapplyo is using defaults to the R option MC cores. So the user can then, when they call, before they call the function, say, I want to use 4 cores. And then when they parallelize, mclapplyo will acknowledge that and use 4 cores to parallelize. So that's another thing you see in R packages. It's a third alternative, of course, for an argument. So here, you user call align all. They will pass 4 cores, and if then you pass that argument down to this option. So that's quite a common design pattern too, you see in R packages. Okay, so then you get your first Windows users coming about and say, hey, I want to parallelize. And you have to start thinking about that. So now you expand your align all function to support Windows 2. And it will look like this. You check if you're running on Windows. Then you go and use this other framework where you create clusters. You want to make sure you stop the cluster when you're done. You load the libraries and the packages that the workers need to have. And if there are global variables and other objects it needs, you pass them on to. In this case, they're actually not needed, but I show it here. And then you call parallelization on those set of workers. So now we can support Windows, Linux, Mac, and sequential processing. And then someone will say, hey, I got 3 machines in my lab. I want to parallelize on those machines. Then you have to expand this again, because this is code we see here is only for local parallelization. And you start expanding and growing in feature request, and you get more and more. And this becomes kind of a big thing. You remember in the first sequential version, we just had a single lapply call at the bottom. And now we have all this other clutter. And if you've done a bit of development, package development, you start worrying, will this actually work? How do I test this? What's my test coverage? So for sure, there will be bugs here. And so you just have to rely on users reporting bugs, and the users have to wait for you to fix bugs and things. So this, you see these solutions too in our packages, but a lot of people give up before they get this far. I went down this path in the Roma project, and that's why the future framework came out. So the solution to this is to actually abstract this away and provide some kind of a higher level parallelization framework. And if I'm quoting the BioC parallel vignette, which applies also to the future framework, the basic objective is to reduce the complexity faced when developing and using software that performs parallel computation. Aims to provide a unified interface to existing parallelization frameworks, infrastructure where code can easily be executed in different environments. So that's how we solve that problem. Each developer, package developer, should not have to deal with this. We should encapsulate that for them. So that's, I say, welcome to the future. It's if we look at the various existing parallelization frameworks, they have a lot of, if you look at the parallel function from the parallel package, we look at for each from the function from the for each package, we see the BPLapply and the BioC parallel, and there are other MapReduce APIs that can support parallelization. They all have common needs, strategies, and implementations. They all want to provide a familiar MapReduce set of functions in a unified API. Slightly different styles, but when users start using them, they will recognize them. They also have this idea of, I want to be able to provide alternative backends for parallelization. They do provide ways to do efficient iteration and chunking. And some of them try to load packages and identify globals and export them automatically, or provide functions for doing that. And then we get into things like handling errors and warnings and outputs, and random number generation, and so on. So the gist of the future package is to serve some of those needs in a common way. It's a unified low-level API. It's not low-level in technical, but a minimalistic style. It doesn't do chunking and things like that. It provides a generic way of using parallel backends. It's loading packages and globals to be exported, handling errors and warnings consistently, and there is also features to protect against non-exportable globals. I don't have time to talk about that today, but it's there. So this is implemented in our package on CRAN since 2016, I think. The idea is to write once and run anywhere when you do parallelization. 100% cross-platform. It's implemented in pure R. Works with any type of parallel backends, even the ones that yet hadn't been developed, I would say. It's a very simple API, easy to install, and I claim very well tested because it's been used in the background throughout a lot of projects and packages. It's meant to give low friction for developers and users. So it's automatically identify global variables and export them. It handles standard output, messages, warnings, errors in a unified way, regardless how you parallelize. And it also provides a foundation for doing proper parallel random number generation. So what is a future? A future it's first of all, this is a concept that was invented or discovered or developed in the mid-70s. So it's been around for a while. A future is an abstraction for a value that will be available later. It's a programming concept in abstraction. The state of a future is either unresolved or resolved, and the value is the result of an evaluated expression. Okay, so what does this mean? So let's look at a basic R assignment. So this looks like a one-line single statement, but if you look at it from R's perspective, it's actually a two-step thing going on. R will take the expression, which can be very complex, or it can be very simple as 1 plus 2, or it can be a big expression. R will take that expression, it will evaluate it, and it will take the value, and in the second step, it will assign it to the variable v. So the future framework allows us to look at this expression in the two steps. And the first step is where you create a future. So you call the future function on that expression, and you get a handle to the future, not the value, to the future. And if this future is allowed to be evaluated in the background, it will just continue in the background. And then when you're interested in the value, it might not be immediately after, it can be further down in your code. You say, hey, I want the value of this future, please give it to me, and then you get the value. So this is a very powerful set of constructs. So let's take a very simple example here. We know this example is summing the numbers 1 to 100. Addition is such a thing that it allows us to parallelize it. Not all algorithms can be parallelized, but this one is, we know that we can calculate the sum of the first 50 and then calculate the sum of the last 50 and sum them up. So if this is a very slow function, it takes 2 minutes to do the 100. It would take 1 minute to do the first 50, 1 minute to do the second 50, and in the end we can sum them up and get the results. We didn't gain anything here at all, but this is the first step towards parallelizing a task. So in the future package, we can tell the framework to say, I want to parallelize on the local computer. You do that with the function called plan and say multi-session. And after that, we can create a future for the summation of the first 50 elements. And the future function here will now just create it, spawn it in the background, and return immediately. So for your point of view, this will take 0 seconds. Same with the second 50 elements. And we're back to our prompt, and we can do whatever we want while these two things are calculated in the background. And say later, 55 seconds later, we want to ask what's the value of the first future. You can do it in any order, but here I choose to do the first. It will block for 5 seconds because there's another 5 seconds to go before it's finished, and then we get the value. And about the same time, the second future will finish. So that would be instant, and we can calculate some. So here, the end result here, we spawn things up in the background, and we finish 1 minute sooner. And the thing here with the future framework, the user has lots of options to parallelize. So the default is sequential. The user can do multi-core, which is the mclapplyo machinery. Can use multi-session, which is the Parallelization or Snow. Some people know that. You can parallelize on 3 local computers. You can parallelize on 1 local computer and 2 remote. You can use a job scheduler to parallelize. You can use the call R package, which works similar to multi-session in this sense on the local computer, and so on. More backends can develop in the future. That would just work. I also want to say that the future frameworks takes care of the global variables automatically. So you often don't have to worry about exporting things and loading packages. You can do it if you want to, but it often works by itself. Here is an example where we create a future that calls the slow sum on a vector x. And what happens the future function will actually do static code inspection in this, and it will identify there is a function called slow sum, and there's an object X. And if slow sum would be part of a package, it would know that I need to load that package on the workers, or I need to export the function. So it inspects the code and sends off what needs to be sent off. And that works remarkably well, actually. I was surprised, but it does work. Okay, so I talked about the future function, and I talked about the value function. There's another function in this future API called resolved, and it allows us to query a future and say, hey, are you done or not? And it does so in a non-blocking way. So with only these three constructs, we can do very powerful things. We can build up higher abstraction layers, and even with just future and value by themselves. So here's the first example. This is your own, very first own parallel lapply. And this is real code. And it emulates what lapplyo does, but it does it in parallel. And it does so by taking for each element in X, it calls the function on that X with the optional arguments, but it does so within a future. So this first construct will create a lot of futures, and basically happens instantaneously because these are spawned off in the background. They will block if you don't have enough workers, so they will wait for that. But conceptually, you can imagine this happens instantly. And then at the end, you just say, hey, now I'm interested in the values. And so before this function returns, all values will be collected. And from the outside, it will work just like lapply. So you would use this library DNA seek. You say, let's parallelize on the local computer, and it will work. And if now a line function would be part of another package like DNA seek, and the future API will know that the workers need to load that package. So that will all be taken care of automatically. So, and then if we want to do a little bit more fancy things like load balancing, random number generation and stuff, we have to do more work. But so there is the future.apply package, which encapsulates those tasks and provides an API for all of the base R's, lapply, vapply, replicate, and so on in the future framework. So if you have code that calls lapply, you can now just call future_lapply. And you can choose how you want to parallelize: local computer, local machines, or in a job scheduler. And here is an example if you wonder what happens with a job scheduler. So there's another package that just provides a backend. It's called the future.batchtools, and it builds on top of the batchtool package. You just specify you want to use that as your parallelization backend. You get your list of FASTQ files, and you call future.lapply. And that will just happen automatically in the background. It will spawn them off on the scheduler and collect the values. And if we peek at the scheduler in the terminal, we ask slurmq what's going on. We can see there are 2 jobs here, and they were all initiated by the future framework and the batch tool package. Similarly, if you like the per API that has map2, modify, etc., there's the fur package that provides futurized versions of the per functions. There is the for each package, which a lot of people know about. It's been around in the parallelization world for quite a while. There's a do future backend that lets you use for each on top of the future framework. And here you have to say register do future. That will tell for each to use the future framework, and then in the future framework you decide how you parallelize. So the point here is that you can stay with your favorite coding style. If you like base R, you can use base R. If you like tidyverse, you can use tidyverse. If you like for each, you can do that. And also you can do BiocC parallel. So you can do that through the do par param option in BiocC parallel. So you tell it BiocParallel to use do_par, and then you tell do_par to use futures, and then in futures you say how you want to parallelize. And then you can use BPLApply or whatever function you have in BiocParallel on top of the future framework. And I would say you can use BiocParallel with future because it provides a consistent behavior regardless of parallel backends. Standard output is truly relayed. I will show that soon. Messaging, warnings, and conditions are also relayed as is. Won't have time to go to it, but there is the progressive framework provides a uniform way to do progress updates in a near live parallel fashion. Even regardless if your workers runs on a computer across the world, you will get those progress information relayed back to your main computer. Okay, what about output warnings and errors? So they behave consistently for all parallel backends in the future framework. Final toy example here. Imagine we have a vector of 3 elements, -1, 10, and 30, and we call log of those elements using lapply. But we also use message to show what the current value is that we evaluate. When we do this, we're going to see output like this, -1, 10, 30. That's from the message. We're also going to get a warning because log -1 will produce not a number here. If you use mclapplyo, this will work with various success. And depending on your environment, your terminal, RStudio, and so on, you might not see anything here. And you won't get the warning. And if you've done parallelization, you see this is like quite hidden. With the future framework, this would just work. And here I'm using future lapply. It could be future map or for each, it will work the same. So the messages are relayed back to your main computer, even in parallel processing, and so are warnings. Let me show you with the BiocParallel, and I'm using this as an example because you might be familiar with that. But the point is this is a common problem that hasn't really been addressed in a standard way. So if we use the BiocParallel and we use the Snow backend, this example is meant to illustrate that although the output is displayed, in this case in my terminal, it's actually not sent to me in R as a terminal. It's happened to be shown in the underlying terminal, because if I try to capture this output, it turns out it's not captured at all. There is nothing is captured, but it's displayed for the fact that the terminal relays this for you. And the same way, the warning is displayed in the terminal, but not in R itself. So that warning can't be captured with try-catch, for instance, or with calling handlers. However, if you use the future framework, so this is how you do that with BiocParallel. You say do par param and then register to future. And then we parallelize however we want, in this case on a local machine, but I can also do it on a scheduler. The same result will work. The output from BPLApply, using BPLApply and calling that function, str and log, will be captured in my main R session, and the warning will be a true warning in my main R session. So that's what you expect if you use a regular lapply. And this is also how it works if you use the serial param setup in BiocParallel. So all this is encapsulated in the future API. So there are a lot of things on the roadmap here in the future framework. Everything done and introduced is done in a backward compatible fashion. So basically whatever code you had 4 years ago will still work. We're just making it better. One thing that is on the roadmap very soon is to have a MapReduce future API. Because if we go back to this thing and we look at Parallelapply for each, BPLApply, but also future apply for do future, they all do things like iteration and chunking and parallel random number generation, which is super important in statistics. And also very fancy things like error handling. What should we do? Early error as soon as we detect that and kill existing workers, or should we provide a way for retrying when it fails? I know for each has some of that. BiocParallel has some of that. So the goal is to add another layer of common tasks, not all of them, but some, so that it would be easier to write those higher level localization frameworks without having to deal with this tedious lower level things. And from the end user's point of view, wouldn't really matter which one you use. On the top, you can use your favorite coding style, and you would expect the same behavior. Now, I should also say that a lot of this code is already available inside future.apply and for do future. We just have been cut and pasting things across, so we want to bring that out to a package that other package developer can use. Okay. So the take home here is don't be afraid of parallelization. And with the future framework, it tries to make it worry-free. And the motto is write once, run anywhere. Global variables should be automatically taken care of. There are corner cases you have to think of, but most of the times it works. Standard output messages, warnings, and also progress updates are captured and relayed back to your main R session. Users are the one that decide how to parallelize in this framework. As a package developer, you don't choose that really. We can discuss that later afterwards. But the thing is, you decide as a developer what to parallelize, and the user decides how to parallelize it. It's 100% cross-platform code. I say it's future-proof because there are backends that are still to be developed that I can't imagine. But as long as they provide the low-level functions called future, value, and resolved, they will automatically plug into this framework. So if someone writes a parallel backend for computing on Amazon Lambda, that will just work here. So please go and try it, and feedbacks and bug reports are most welcome. I would end my talk there. Thank you so much.
Thank you, Henrik. That was a great talk. I really enjoyed it. So just as a reminder, please, we're not going to use the raise hand feature, but use the Q&A box for questions, and I will relay those to Henrik. But and I see already a couple of questions in the box, but I want to ask one first, which is, what I usually struggle with when I do parallel computing is to decide what to export to the workers, right? Either explicitly or implicitly. And sometimes it happens implicitly, for example, with mclapplyo. And so if I use the multi-core backend in BioC Parallel, it works. But then when I switch to snowparam, it will not work because that will not export. So maybe it's out of the scope of the future package, but since you mentioned at the beginning that the goal is to make it easier for package developers,
Yep.
How do you, do you have any advice on this?
So if you use the future package, it will most likely just work. I'm not claiming it works every time, but so the idea there is like it will lower the friction to get started. And then when you start looking when you start, that's you don't want to turn in the door when you start using Parallelization because you like Windows users won't get your cool function in parallel then. But get people in the door, and then when it comes to like fancy optimization, there are ways to look into that and might be able to improve it. But there are things like you should not export all of your matrix if you only operate in the first column. So that's also these higher level map reduce APIs take care of that for you. But there are structures we're thinking about how to provide that too. But yeah.
Awesome. All right. So the most upvoted question, actually, it's a pretty straightforward question. Can you post the link to the slides?
I will. I will do ASAP afterwards.
All right. Great. That's awesome. So then we have a question by Vince Carey. Planning a feasible memory footprint seems important. Do you have example on how to instrument usage of this framework?
I'm not 100% sure what instrument usage of this means.
Yeah, it was in quotes, but...
I read now. I can see it here too.
Okay, great.
I just have to guess unless I get a clarification. So that,
you want to switch to move to the next one, and then we can ask Vince to clarify?
yeah, let's do that.
Yeah.
It's yeah,
Okay, so we have one by Chong Tang. Can we manually assign the computations over several workers managers to make sure the computations won't have conflicts in Linux and Mac?
Again, I'm not 100% sure what is after here. Computation of several workers. So the user, the idea with the future framework is that the user decides. You, as your package developer, you don't know what compute resources the user has. So you can't say, I want this one to go to this machine and this go to this machine in the future framework. However, there is on the roadmap too something called resources. Similar you find in job schedulers. And this is like we have to figure out how to declare those. But you can imagine this, you can specify in your future that this future should only run on the local machine. It doesn't make sense to export that somewhere else. So if you can specify this resource should be on the local machine, or this resource needs a GPU, or it needs a genomic reference file, and then it will only send it to the workers that has that reference file.
Yeah, that's great.
But not like send it to this specific machine, because you don't know what that specific machine is. Yeah.
All right. So we have one by Dario Righelli. Do the APIs provide also a way to combine the results of the parallelized computations, i.e. cbind, rbind, etc., or maybe providing a user-defined function for combining the results?
So at the low-level Future API, not. So it's basically very pure R without having access to things like lapply and things like that. So that comes into the higher level APIs that's meant to be implemented elsewhere. There are certain things, but basically it's very low level basic.
All right. So we have the clarification, I think, from Vince. Measure the impact of choosing the number of cores, say.
Okay.
As you add more jobs to run in parallel, you will eventually exhaust available RAM. Do you have ways of helping users to assess this risk? Sounds like your resources discussion is relevant.
Yep. So that was actually my first guess of the interpretation of this. Yeah. So no, there is a little bit there. So for instance, if you look at the basically now deprecated Snow package, I think it's the Snow package. It has a way of it collects actually some data when it started and stopped, and the future framework does that. It doesn't expose it to you, but it would be nice to be able to show graphs. It's like time graphs. It's like when did the different workers run, and also ideally measuring how much memory each of them works.
Yeah.
And there's some work on measuring memory is really complicated, but let's say it's on the roadmap. It's collecting some of the data at the low level. It just doesn't present it. But if you go in and inspect the objects, you can find some of that information.
Okay. And then another comment from Vince. Learning about plans seems the main first step. Do you agree with that?
The options to do plans, I would say, most people would everything runs sequentially. And then most people will just run with multi-session. We recommend locally in your computer. And then doing it across your local machines and in your lab on remote machines actually works very simple. It's very simple as long as you have SSH access and R, it will just work. Yeah. So it's, I don't know if it's complicated. Future batch tools and those things, that's where people struggle. Set up templates and things to submit jobs.
So I think we're right on time, and the chat box is empty. So I'll thank again Henrik for his great talk, and
thank you.
I hope you can see all the emojis reactions.
I do see. I've been watching that.
I hope they were not too distracting.
It looks like Wolfgang is getting all of them now.
All right, so next up, actually, we have Kevin Rue-Albrecht that will give us a quick update on the BioChallenges that were going on over the week. So, Kevin?
So, right, thank you, everyone. It's great to follow up on a keynote talk like this. We'll see if I can keep everyone interested for the next 10 minutes. I've got the number right there. And so this is not just a repeat of the first talk that you've seen on Monday, but more of a closing talk to let you know about what happened during the week on the conference platform and outside with regard to the BiocChallenges, so for Bioconductor challenges. So I want to thank Charlotte and Laurent who helped me craft the package and shape it. So initially it was just a nice set of R Markdown document tied into a nice website, but now it's actually a fully fledged Bioconductor compliant package. And yeah, so I'll show you how the vignettes look like. There we go. I also want to thank, so this is a list of people I've interacted with over this week. There's also, so Mike, who led a discussion about the GitHub action. So there was a bird of a feather, and we've discussed a bit about it. There's no direct consequence in BiocChallenges because one of the outputs is that there's the BioCDs package by Leonardo Corrado Torres, who provides a GitHub action, but it definitely provided a nice framework for discussion and gathering interest in that direction. And then Charlotte, Laurent, Jérôme, Mike, and Kun got involved a bit. Well, I'll show you in the next slides, but this is really just to acknowledge people who have contributed one way or the other to the BiocChallenges. And I think I may have missed a few also already. And then, yeah, on the right side, I wanted to mention, so there's been a bit, the topics that were discussed were the GitHub actions for Bioconductor, transcript visualization using IC, and spatial challenges. So again, I'll get to that in a few slides. So that's how so using the package down package, I'm turning this package looking repository into a package down website. And so you have, that's the landing page. You've got the getting started to tell you that will guide you how to contribute a challenge if you have one in mind. And if you're looking for examples, it's going to be in the article section here. So you can see the ones that are listed. And I wanted to emphasize that this unlocking IC for transcript level visualization is an addition from this week. And I mentioned Vince also on the previous slide as he contributed in a challenge a couple of weeks ago about the instrumentation for genomic computing with Bioconductor. So I've got a later slide to just give you a bit more detail about this. Yeah. So anyway, it's growing, and so each of those challenge listed here is essentially a vignette. So if you've seen a Bioconductor package before, you know what the vignettes are, and so I'm using that structure to essentially write one vignette per challenge. And when they get compiled, that's how it looks like. And so this is to emphasize the new challenge about unlocking IC for transcript level visualization. And there's a bit of detail here. Jaren has taken the role of challenge leader. And there's also a link, which I think is out of screen, unfortunately, which will point you to the GitHub repository where we started essentially the scaffold of a Bioconductor, of an R package. And yeah, so there's already a bit of activity there. So I wanted to mention a new challenge that was a bit before the conference. So from Vince, essentially having a system for estimating resources needed for genomic analysis activities, which I think ties back to the question he was asking just now. So maybe Henrik and maybe some other people want to get onto that issue, that challenge. So it's all listed there. And the point being that there's a challenge leader, and if you have any question, if you wonder about what does it mean, if you're interested in it, but you want to see more details, the challenge leader is there for that, to act as a point of contact. And yeah, there's been also a bit of an update on facilitating the diagnosis of Bioconductor package build failure. So this is one started by Charlotte Sonson. And there's been a bit of discussion on the GitHub repository, which is not visible in the screenshots. But so there's some progress. I'm just glad to see that the challenges are sort of showing some activity. There will probably evolve. I'm really open to updating the format of the page because there may be more maybe people want more information about the challenges. Maybe those categories are not sufficient. So it's work in progress. Just today, I was adding something to look at the latest commit on each contributing repository to kind of show signs of activity without having to browse GitHub yourself. And so I'm kind of proud and glad to see that the BiocChallenges has inspired a separate repository because there was some discussion about this challenge of spatial transcriptomic analysis. And when I see that they already have 11 challenges on their repository, I'm sort of glad that they've started a spin out of the BiocChallenges, because otherwise it might have overwhelmed and people would say, oh, BiocChallenges are all about spatial challenges. So it's nice to see. It's an idea. So maybe later on we'll find a way to integrate the two repository, or to integrate the spatial challenges under the main one. But I think it's nice to see an initiative about this. And I've got a point slides about maybe we want to have sort of to franchise the BiocChallenges and have families of challenges, of thematic challenges. All right, I'm going to wrap up soon. So I mentioned that already. So your feedback, you're welcome. So I've so far designed the sections of a challenge vignette. Maybe you have an idea about more sections to add or how to make them more useful. And yeah, more functionality. So the BiocChallenge repository comes with some R code that does all the GitHub browsing for you. And yeah, more thoughts. So I don't know yet how I feel about like spreading into the challenges into too many places, but why not having, I don't know, a BioC microbiome challenges, BioC gene set challenges. So in that regard, I've created a GitHub template repository, which is a relatively new feature, but I've essentially written a template that people can use, a repository that people can use as a starting template to write a BioC spatial challenge-like repository, so that it comes already with all the functionality. It imports the main BioC challenge repository so that everything clicks in place. And that's because it's a challenge, it's a package, it provides function, and the template declares an import to use those functions. So that's just a rehash of what I've said at the start of the week. So I'm really glad to see that people have networked and communicated with each other, really in an open conversation, getting the ideas flowing, what works, what doesn't work, what already exists. For example, as we said in the GitHub Action, BioCDs. So I'm really, really glad of what happened this week. And so that's why in the title I did have and beyond, because I don't want that to stop or to happen only every 6 months at Bioconductor, but it would be really nice if it continues between. So yeah, and with that, I want to thank everyone in the Bioconductor community, essentially. So I'm citing the paper, but it's really the whole community that I want to thank, which makes this kind of initiative exciting. And yeah, and I really look forward to what can come out of it.
Great. Thank you, Kevin, and thank you to everybody that contributed to the challenges this week and beyond. Are there any quick questions for Kevin? Oh, maybe there is one. Do you plan to add the BiocChallenge Slack channel?
I was thinking about it. I'm just wondering, because in a way, there are some thematic channels on the Bioconductor Slack, about spatial omics, about different things. So maybe the challenges will naturally fall into those different channels, but I don't have any problem about creating another channel if, I don't know if it's to coordinate the challenges.
That could be a good scope for the channel. Yeah.
Yeah. Channels don't cost much, right? So it's if, for example, people told me that it would be really nice if the challenges could be presented at conferences or lead to workshops or birds of a feather. So maybe having a channel for coordinating those events across challenges, while the individual challenge will go into potentially separate channels.
Great, thank you so much, Kevin. All right, so Wolfgang.
Yes, hello.
Yeah. All right, so I will now leave it to you for the closing remarks.
Thank you very much, Davide. So it's a real pleasure now to share a few words about the closing of this conference and about what happened and what came out of this week. So first, I would like to start with thanking our sponsors, F1000 Research, for providing a lot of the publication infrastructure, the R Consortium, and of course, the University of Padua for hosting this event. So this conference has been by far the largest European Bioconductor conference, actually, so far by any amount. We had 400 active participants, 7 keynote talks, and lots of contributed sessions and speakers. And you can see these numbers. So it's been really an amazing week and fantastic. And it's been great to have so many people involved from all over the world and from all different contexts. A reminder about the posters and slides. So please, to make your posters and slides persistent, please upload them to the F1000 Research Gateway. That's a really nice way to sort of keep this work visible. Also in the future, people will find it in Google, and it's a nice place to upload your work. There is also in general, a gateway on Bioconductor at F1000 Research, which is a really dedicated open access publication portal for all Bioconductor related outputs. The nice thing about this F1000 Research platform is it's obviously open access, and it also has this sort of novel and I think groundbreaking peer review model, where instead the peer review isn't the one-off gatekeeper function, but there's an emphasis. But the peer review is actually happening after and during publication, and there's an emphasis on continued quality control over time. Also, you can have multiple versions of your papers and so on. I think this is anyway the future of publishing in F1000 now. And we're really glad to collaborate with them on publishing some of the Bioconductor outputs. Also, there's a channel now for EuroBioc 2020 exactly to host the products from this week within this gateway. The workshop. So, I mean, these have really been progressed a lot over the course of this year, and in fact, due to the pandemic, there has been sort of this need and also wish by Sean Davis and some of the co-workers to create this amazing platform now that we have as an environment for workshop. It's really been a game changer in running workshops. It makes life so much easier for workshop authors and to develop and deploy workshops, and to really also standardize all of the sort of nitty-gritty of the infrastructure that's behind providing a workshop and or actually participating in it. This is really nice. The workshops from this week will be available after the conference, and sort of the details about this are in the slides. So there's a GitHub repo for each workshop, and this is how you can access them. These slides will of course be linked from the conference program, so you can also find these links via there. One thing that this week also saw and witnessed was the foundation of the European Bioconductor Society. This is now a registered, will be after the court sort of accept all our papers, will be a registered charitable society. Under Germany's law, this is a fairly lightweight structure. It's a bit like your local football or tennis club. And the primary objective of this group really is running the conferences and courses. So it has a current board and some members that you can see here. So obviously, you don't have to be in this society to use Bioconductor. Bioconductor is a completely open project, and anybody that just participates in any of the conferences or on the forum or participates packages is already automatically part of the Bioconductor community. This particular sort of sub-organ or substructure within the community, I hope will be useful in organizing conferences like this one and also summer schools in the future. So what are next steps for you? Well, please do act on the post-conference email. You will also, if you can send us your postal address, you will get the EuroBioc 2020 stickers. And there's also a survey, which would be very useful for us to obviously optimize future events. For your own work, don't code alone, don't reinvent the wheel, don't reinvent the wheel. There's a large community to help. You can use packages, you can develop your own packages building on top of what's already there. and solve your problems hopefully really quickly. There's many different forums to contribute, or ways to contribute. There's obviously the forum on the website to post questions. There's also a Slack channel sort of for more quicker informal interactions. And of course, we want you to submit packages, use packages, of course, and maybe also join the next conferences and events. To stay in touch, this is just a collection of links that will be useful for you to see what's happening in the community. So again, there's multiple different modes. There's a support forum, there's a Slack for all sorts of discussions. There's a Google Calendar with events. There's also a developers forum if you're interested in topics about developing packages. Like the last Keynote slide was an amazing example of the kind of topics that are really interesting and useful if you're developing packages. And here's there's also YouTube channels and a Twitter channel, so you can all find all of these channel ways to get in touch. And this is just a reminder and the link to the conference feedback form. So please do give us your feedback that you have, so we can take into account next times. The next conference will be in Seattle, BiocChallenges 2021. So we're really grateful to the local hosts there, to Mark Carlson, for hosting this, and we'll be looking forward to being in Seattle, be it in person or be it virtual. I think this is also being worked out, and we will see. But in any case, Seattle is a fantastic location, and obviously we had lots of conferences there in the past, and it's always great to be there. That's probably one of the most important slides, to thank all of the organizers. So you can see the people that were involved in sort of conceiving this, designing, making the program, inviting everything. This has been an amazing amount of work. My part was the smallest of it, but I mean, all of the people that you see have really put in an enormous amount of effort to make this happening. So I am really grateful, and I think we can all really be grateful to them. In particular, the local organizers. We should have been in Padova if there hadn't been this stupid pandemic. But we are really still very thankful to the local organizers who put together the platform and were crucial in making this happen. So Gabriele and Chiara and certainly Davide, who put in an enormous amount of presence and effort and work into this conference to really keep the overview. I mean, he is the person where all the threads ran together with Simone. So thank you very much. We also would like to thank Martin Morgan, who is sort of the godfather and sort of at the top of the project. So as you maybe have heard from his talk on Monday morning, he is sort of taking a step back now and letting others sort of take the front row in running the project. His contributions really have been amazing. So he's been at the helm of this project for 11 years now. It has been growing ferociously over this time. It's just some statistics, like the growth of number of packages from 300 to now in the order of 2,000. The number of conference attendees that we get. We have a really vibrant core team that's sort of very competent in making sure that the infrastructure just works. I mean, the good thing about infrastructure is if you don't notice it, it just works, and that's sort of what Martin and his team have achieved here. So this is really not to be underestimated. One of his other big achievements is now the setting in place of a robust, modern governance structure of the project. The project started, I mean, there's many open source projects in a fairly sort of ad hoc and heuristic way. And now with the technical advisory board, the community advisory board, and these various new organs, we have a really robust, inclusive, and modern governance structure. So that's an amazing achievement that he also has. And of course, the things that are I think about most in the context of Martin's contributions is his infallible kindness and his patience. He's also incredibly competent and unfailing. I mean, whatever he contributes or says is just right. And the software that he writes is often complex, but always clever and elegant and solves the problem. He's obviously unpretentious and has a very fine humor that I appreciate a lot. And also I'm really grateful to him for his efforts to make the project sort of more inclusive, bigger, more modern, and more open. So thank you very much, Martin, for everything you have done, and I hope also for everything you still will do in various ways for the project. Yeah, and here's some pictures that show Martin in various ways. So this is something that we digged out of our photo albums. And you can see, obviously, Bioconductor is being such a big project around the world. Lots of traveling. And you can see Martin in various capacities at conferences, workshops, in probably every continent of the world. So I'd like to thank again the organizers and you for your attention. Thank you, Martin. Thank you, organizers.
Thank you, Wolfgang. I think this is a great way to close the conference. And, just to remember that some of us will just hang out in the platform at the virtual tables. So feel free to join us. And I mean, since I was mentioned by Wolfgang, I should say it was a great pleasure to organize this conference. And it is true that it was a lot of work, but it was with a lot of fun people, and I'm really tired, but really happy on at the end of this long week. So thank you for your support, and thank you all for coming and making this a wonderful conference.
Thank you, Davide. Thank you, everybody in the committee.